Good. Good. So good afternoon, everyone, and welcome to Kate Alexander's Public Thesis Defense talk, Cosmic Extremes, Probing Energetic Transients with Radio Observations. Wow. So before I turn the stage over to Kate to tell you all about her work over the last few years, I just wanted to share with you a few facts and observations about Kate. So Kate came to Harvard in 2012 after receiving a bachelor's degree from Brown University. And she spent the first 2 years working with John Kovac's group on the CMB, and in particular in simulating B modes. And during that time, she also spent about 6 weeks at the South Pole. And if you haven't had a chance, I really recommend reading her blog from that time, titled Kate Goes South. I found it kind of fascinating, and she has some incredible pictures that give you a sense of what life there is like. So Kate then joined my research group in 2015 to work on radio observations of astrophysical transients. And right away she had great success with the discovery of an outflow from a nearby tidal disruption event that demonstrated, I think in a really nice way, that when a supermassive black hole tears apart a star, not all of the material gets accreted onto the black hole, some of it actually gets blown out. And you'll hear about some of this today. Kate then spent a substantial amount of time working on observations of gamma ray bursts as part of a VLA large program. There was about 210 hours of telescope time, and she had the privilege of analyzing a lot of these data, which was quite time consuming, but again, it, I think led to some really interesting results that she'll tell you about today. And then most recently, Kate played a really important role in some little discovery related to gravitational waves that you may have heard about. And in particular, she led our group's observations in radio and millimeter using the VLA and ALMA to study this event. And in fact, Kate was the first person in the world, and for all we know in the universe, to set radio eyes on this binary neutron star merger. So she observed it 2 hours after the event was localized and got the first observation. So I think she has that distinction and privilege. So just stepping back for a moment from the science, which I think is incredible, and you'll see it for yourselves today, I just want to say it's been extremely rewarding to work with Kate over the last few years. She's a fast thinker. She's a great collaborator, and a real pleasure to work with. And she brings a lot of energy and enthusiasm to her work and to the projects that she's working on. And so that made my life a lot easier as an advisor, and I think it was a lot of fun for everybody in our research group to work with Kate. So going forward, Kate is going to be an Einstein Fellow at Northwestern University starting next year, which is going to be really exciting. But for now, I'm going to turn things over to Kate, and we'll hear about cosmic extremes.
All right. Thank you very much, Ido, for that very nice introduction. As Ido said, we're going to learn about cosmic extremes. But first, I wanted to take this opportunity to start out this talk by acknowledging some of the people who have helped me get this far. I want to start out by acknowledging Ido. Thank you, Ido, for being the best thesis advisor I could have possibly hoped for. Don't worry, I'm not actually going to play the video. But the first opportunity I had to work with Ido, I actually was the teaching assistant for his undergraduate observational astronomy class. And as part of this class, the students get to go on an observing trip over spring break. So there we all are down in Arizona. And as you can tell from this picture, we learned a lot about what astronomers do when the nights are too cloudy to actually see anything. But this, nevertheless, the students were so inspired by this class that they felt motivated to use their cloudy nights in the dome to create a musical ode to their wonderful instructor, Ido. And I didn't include the link down there, so if any of you in this room haven't seen the video, it's clearly made an impact. It has over 800 views on YouTube, so it's I think it's a testament to Ido's excellent qualities as an instructor. And they were very sneaky about filming it, too. This is them sneakily filming us in the airport. We had no idea they were going to use this in the video, but anyway. I'd like to thank Ido also for just being the most supportive research mentor I could have asked for. I've really learned a lot from him, and he's made sure I've had the opportunities to go to a lot of really great conferences and meet a lot of other leading experts in the fields. He's provided office space when the sky decides to do something particularly exciting. This is from last fall, right within 24 hours of when the gravitational wave event was discovered, and a bunch of us were so excited we were camping out in his office at 11 p.m. on a Friday night. So thank you for donating the office space and the money for the pizza that kept us going and science progressing. So it's been a real privilege working with you, and I'm looking forward to continuing to collaborate in the future. I'd also like to take a moment to thank my other research mentors who have helped me throughout my time in graduate school and also before graduate school. Ido mentioned that I started grad school working for John Kovac, and I really enjoyed my time in his group, and I want to thank him and all of the members of his group for teaching me so much about how instruments actually work, which is a very useful skill, even though I no longer am responsible for putting them together myself, which is probably a good thing. I'd like to thank Alicia Soderberg, who was my first mentor in the field of radio astronomy. When I was an undergraduate, I did a summer RU project here and looked at some radio observations of a supernova. And I didn't know that that was going to become very relevant to my thesis then, but I'd like to credit her enthusiasm and mentorship with helping set me on this path so many years ago. I'd like to thank my faculty mentor, Sean Andrews, for useful discussions over the past couple of years as I've gone through this writing up the thesis and job application process and all the fun times that go along with that. And I'd also like to thank my undergraduate thesis advisor, Jan Del Antonio, who was a graduate student here himself many years ago and was really very supportive back when I was studying physics in undergrad and deciding to come to grad school and pursue this as a career. So I'd like to honor him as well. I'd like to thank my thesis committee for being here today to share this research with together. I'd especially like to thank Ramesh for being the chair, even though he didn't know it while he was on sabbatical. It's been great to discuss my ongoing research with all of you. And I'd also like to thank Dale Frail, who's here all the way from New Mexico to serve as my external examiner. I really have had the best colleagues and collaborators in a research group over the past couple of years as I started working on my thesis group. I wanted to call out everybody or people individually who I thought I worked especially closely with, and then I realized I could say something very unique and very nice about the collaborations I've had with every single person in this photo, and also the additional people who are listed at the top. But it's been really a lot of fun to work with you all and to hear about what you're doing when it's different from what I'm doing. I do want to thank Ashley Zauderer, who helped me get started on studying tidal disruption events, my very first project in my thesis. She was a postdoc here and now works for NSF. And I'd also really like to thank Tanwai Lasker, who was my first guide into the many myriad facets of gamma ray burst explosions, and also helped me get started with this rapid turnaround radio observations that we need to do whenever a new GRB is announced. So we had split duty where one of us would be on call. If a gamma ray burst went off, we had to drop everything and put in the observations. And it's really been a lot of fun working with him and with everyone. And I'm going to miss you all, but hopefully we can continue to collaborate in the future. I'd also like to thank all of the graduate students and faculty in the department here who made my experience as a graduate student here so wonderful. I think one of the really special things about the Harvard program is what a great sense of community there is among the graduate students, and how people do things together outside of work, and you have plenty of people to, bounce ideas off of who are not in your immediate research group. And I feel like I've formed a lot of really special friendships here, and I just want to thank everyone in the department, both those in this picture and those who are not in this picture. And I especially want to make sure that I give thanks for our wonderful, wonderful administrative assistants, without whom this department would not function, especially Peg and Rob. Thank you so much for everything that you do for all of us. It is deeply appreciated, and I think most of us would not have made it this far without all of your help. I do also want to thank my non-astronomy friends who do things with me outside the CFA sometimes. You have made the parts of graduate school where I'm not working be a lot of fun, and also put up with me sometimes when I am working on during what you thought was going to be a fun vacation with no work. But I've had great opportunities to travel to a lot of places and do a lot of fun things as part of my graduate work as well. And friends really are one of the great things about being here in Boston. So thanks to all of you. Finally, I'd like to thank my family, some of whom are here today. It's so wonderful to have all of you here, to be here with me at this point. I definitely would not have gotten this far without all of your love and support. And thank you also to my family who could not be here but are watching this live stream from as far away as Colorado and India and California. I'm thinking of all of you, and it's just been so incredible to be supported by all of you from all sides. I'd especially like to thank my sister Christine for being a wonderful counterbalance to some of my extreme science nerddom. I'd like to thank my parents who really I could not be here without your love and support and your inspiring example, both to continue studying the physics and also to see the beauty of the universe that I'm studying. And finally, I'd like to thank Sukrit, my partner in everything, who got to see both the ups and downs and really helped me get through the worst of times and got to enjoy the best of times with me. And I'm really looking forward to continuing adventures with you. So now let's move on back to science and talk about cosmic extremes, probing energetic transients with radio observations. Well, that, as Ito alluded to, that's a little bit of a mouthful of a title, so let's break it down. Cosmic extremes. What are the extreme things that we are interested in talking about? Well, we're interested in learning about how do you accelerate material to very, very high speeds, relativistic velocities near the speed of light. Sometimes when a one-off transient event happens, like a star exploding or a star getting accreted onto a black hole, you can accelerate a jet of material to nearly the speed of light. We're very interested in learning how this happens and studying what this can tell us about some of these most extremely high velocity materials in the universe. We're also really interested in studying extremely dense matter. So there are giant black holes at the center of nearly every galaxy. We'd like to know more about them. We'd like to know how they grew to be that large. And we'd like to know how material actually falls onto black holes and accelerates to high speeds while doing it sometimes. We're also very interested in studying neutron stars, which are the dense cores of dead stars, basically giant balls of neutrons. Occasionally, they will crash into each other. And as we saw last fall, when that happens, some very exciting things result, as you also saw in the movie just there. So we're very interested in learning more about what happens and how these one-off astrophysical extreme events can produce these very unique physical conditions that we cannot reproduce in the laboratory here on Earth. So why radio observations? Well, there's a couple of reasons. One of the most obvious ones is that it's very easy to observe radio waves from the ground. So this is just the electromagnetic spectrum. And the shaded blue area here shows the transparency of the atmosphere as a function of wavelength. So you can see there, we can see visible light through the atmosphere. That's why early astronomers all looked at visible light. But there's also this nice gap in the radio from wavelengths of about a meter down to centimeter, millimeter wavelengths, where we can just have a telescope on the ground, look up at the sky. We can actually observe in the daytime because the sun's not as bright in the radio. So it's very easy to do radio astronomy from the ground, and we can look up into the sky and see what else is out there. If we want to look at these other wavelengths, especially shorter wavelengths, we have to launch a satellite and go to space. The other reason obvious reason you might think that radio is an excellent way to look for these one-off transient events is that the radio sky is very quiet. If you think about the optical sky, you might think about beautiful dark sky photos of the Milky Way, and there's all these stars, there's all this dust, there's a lot of things in the sky. When you look at this picture, this is the extragalactic radio sky, you're probably thinking it's not dark enough, I can't really see anything, there's nothing there. That's kind of the point. All of these little tiny dots here are galaxies beyond the Milky Way, and you get emission from the giant black hole at the center of the galaxy called an active galactic nucleus, or an AGN. Sometimes they emit jets. Sometimes you get radio emission from star formation in the galaxies. But in general, this is a pretty quiet field of view, so you'd think it would be pretty easy to tell when something changes, if a new source appears or disappears. And it turns out that all of these kinds of explosive, extreme transient events that we want to study produce broadband synchrotron radiation, which is radiation that's produced when you have electrons that are moving at relativistic speeds accelerated in a magnetic field. And so if you want to learn more about the physical properties of the system, it turns out that all of these break frequencies and the overall amount of light you're receiving evolve with time and depend very sensitively on the physical properties of the system. So if you can measure the synchrotron spectrum of an emitting source, you can learn how much energy is in the emitting source. You can learn the density of the medium it's expanding into, which can tell you about if it's a star exploding, what the last years of the star's life were like. If it's around a black hole, it can tell you something about the black hole's accretion history. You can learn something about the shock physics of the shock that's actually doing the particle acceleration to get your synchrotron emission. To fully characterize the spectrum, you need observations at wavelengths from the radio and all the way through the optical and the X-ray band to fully characterize each of these break frequencies. The radio is particularly important because at early times, this break here, nu A, which is the synchrotron self-absorption frequency, is in the radio band, and then at late times, the peak of the emission will actually move through the radio band. So it's very important to not just have optical and X-ray observations. You really want to look in the radio where this emission is the brightest and where there aren't a lot of other confusing, or not as many confusing background sources to be confused with. This is an example of how this works in practice. This is a set of radio observations from the millimeter down through centimeter wavelengths of a tidal disruption event. I'll tell you more about those in a minute. That is still visible 7 years after it originally exploded, and you can see that we have this very nice model of the synchrotron emission, and we fit each of the spectral energy distributions. So this is frequency versus amount of flux received in each of these panels, and you can see that the peak starts way up at the high frequencies and moves down to the lower frequencies over time. So we can really constrain directly how the properties of this outflowing material evolve with time, and you build up this very nice density profile on scales of a parsec or less, which at the distance of this object is never something you could actually directly resolve with an optical telescope. So this is a beautiful data set in a sense of exactly what we're doing. So you may ask, why don't you hear all the time about dozens and dozens of transients being discovered in the radio? And it's worth taking a moment to, as an aside, talk a little bit about how radio telescopes actually work. So there are many radio telescopes in the world. These are two that I have used. This is the Very Large Array, or the VLA, in New Mexico. This is ALMA down in Chile. And because radio wavelengths are so long, you need a very large dish to be able to observe the sky at high resolution. So you want to be able to precisely localize where your source is in the sky, so you know what galaxy it's associated with and learn something about the astrophysical environment. But you need a very large field of view to do it. So an interferometer is a clever way of pretending like you have a telescope that is the size of the full array by combining the emission seen by each dish individually in a clever way. And when you do this, you get a high resolution, but you also have a very small field of view. So doing a survey where you survey the whole radio sky is very time consuming. It has been done, but looking and doing it repeatedly so that you get identify transients as they occur in the radio band is very time consuming. Our plans underway for the next generation of radio telescopes that are going to be able to do this. But for now, most of the sources we study are discovered first at other wavelengths. Then once we know where to look, we follow them up with these very sensitive instruments with high resolution so we can study their properties in detail. So the types of objects that I studied in my thesis are objects that we know produce radio emission, and once we are able to better characterize their properties of these populations of objects, we'll know a little bit more what to expect, and that'll help us plan for future radio surveys. So that concludes the general introduction and motivation of the topic. Now I'm going to pick out a couple of cool results that came out of various chapters of my thesis, and we're going to start by talking about tidal disruption events. So just to make sure everyone is on the same page, when I'm talking about a tidal disruption event, I'm talking about a star getting torn apart by a supermassive black hole. As the star comes in on its orbit, it eventually will reach a point where the tidal forces from the black hole are stronger than the star's self-gravity. The star gets ripped apart. About half of the material will remain bound to the black hole, and so will eventually fall onto it, forming a hot accretion disk as it does, and sometimes an outflow or a jet of material. So when we're studying a tidal disruption event, what we're really seeing is the light from this hot gas as it heats up and falls onto the black hole. And also in the radio, what we're studying is any emission from the interaction of some of this material that gets blown out in a wind or a jet as it falls on. It's also possible, under certain parameters, to perhaps observe the material that was unbound interacting with the ISM, but that usually does not produce enough radiation to compete with the rest of it. So this is a toy model of what the outflow looks like. So kind of zooming in on the very center part of the previous picture, you have your black hole in the middle, your debris coming in and forming an accretion disk. And then if the black hole is accreting material rapidly enough, it actually can't have all of the material just fall directly onto the black hole. Some of it gets blown out in a wind. And under certain conditions, you might get a narrow collimated relativistic jet. Part of the motivation to study these objects is to figure out what conditions are required for the jets to form. They may require particularly strong magnetic fields or particularly high accretion rates or other things. We don't see jets in every tidal disruption event. But more tidal disruption events are expected to produce this slower outflow of material. And this particular paper that I borrowed this figure from was arguing that depending on your viewing angle, what angle you're looking at this system, you will see the emission peaking in the optical or the X-ray, depending on how much material is there for the hot center of the accretion disk to be reprocessed before we see it. So this was the status of radio observations of TDEs when I started my thesis work on this area about 3 years ago. There were a handful of TDEs that had very bright radio emission. One of these, the red one, is that very nice data set I showed a couple slides ago where we have this very nice multi-frequency radio coverage over many months. And so these ones we think are, in this particular case, we are looking straight down the axis of the jet, so it appears really bright because it's pointed right at us, and a mildly relativistic jet of material was produced during the accretion phase. However, there were also all these upper limits shown by the gray triangles that people had at late times, which show that for the majority of TDEs, I think there's about 15 events on the plot of this stage, they didn't produce radio emission that was anywhere near this bright. So we can already rule out that all of these events produce jets like this. So we knew that only some TDEs produced jets, but we didn't really know what the rest of the population was doing. So a big part of my thesis work has been starting to fill in the lower half and the earlier half of this plot here. So this event, Assassin 14Li, is the one Ito mentioned, and I'll talk a little bit more about it. Then there was another event discovered by the XMM Newton SLU survey, which also we found to have faint radio emission. And then we also have some upper limits at very early times and faint luminosities, indicating that it's still clear that only maybe a few percent, maybe up to 10% of TDEs produce these relativistic jets. Some additional amount of TDEs produce these weaker radio outflows, and some TDEs may not produce radio emission at all. So we're still trying to understand the full range of TDE radio luminosities and what conditions are required to form outflows. But let's take a detour and talk a little bit more about my favorite tidal disruption event, which is called Assassin 14 Li. This TDE was discovered in the optical by the Assassin survey, which is designed to look for supernovae, but will also discover bright transients in nearby galaxies. It has an optical spectrum that's pretty typical for optical TDEs. It has these broad emission lines in hydrogen and helium. A lot of TDEs have an excess of helium-2, which says something about the ionization state of the gas, most likely. It also didn't evolve like a supernova does. This just shows the spectral energy distribution as a function of time for this event, and it remains very hot over a period of nearly a year. Supernovae will usually expand and cool, so you would see the peak of this moving toward redder wavelengths, but instead it stays at about the same temperature. So whatever is producing this emission is remaining hot, which is exactly what you expect for a TDE. So this looked like a standard optical TDE. It also had some X-ray emission. It was nearby, so there's a really good data set of it, so everyone got very excited. And then it got even more interesting when we looked in the radio, because when we looked in the radio, we saw that at early times, this object was very bright at high frequencies, and then over time, the high frequency emission faded and the peak moved to lower frequencies, which is exactly what you would expect if there is an outflow of material that's producing synchrotron radiation and interacting with the surrounding medium. And there was some other unrelated radio emission also in this galaxy. So that's the dashed line in the left plot, and then I've subtracted that off in the right plot, so you can really see better how the radio emission evolves over the first year. So what we did was we fit a synchrotron emission model to this radio data and said, okay, well, since we have this data, we're going to just see what are the properties of these outflows at these different snapshots in time, and then use that to infer how the synchrotron emitting material evolves with time. So when we do this, we find that the outflow, depending on exactly whether you assume it's completely spherical or some cone of not perfectly spherical, but more like a cone of emitting material, you find that it's moving at a constant velocity of about a few to 10% of the speed of light, and it has a constant energy of about 10 to the 48 ergs. So this is a lot slower than the relativistic jet, which is moving at almost 100% of the speed of light that we saw in the really bright events. But you expect, in fact, exactly this kind of wind to be produced if the black hole is accreting at a rate that's above the Eddington limit, but not very far above the Eddington limit. So what we did is, since the outflow is moving at a constant velocity, we could extrapolate back in time and figure out, okay, when was the size of the emitting region 0? When was the outflow launched? And we find that the radio outflow was actually launched several months before our first observation. And independently, we had a collaborator who did some modeling of the rest of the emission from the TDE, the optical and the X-ray and the UV emission, and his models predicted that the TDE should have started accreting above the Eddington rate just around the same time when the radio outflow turned on. And the radio outflow turned on just before the accretion rate onto the black hole peaked. So this is very consistent with the general qualitative theoretical picture of how super Eddington accretion onto black holes work. But it's also very interesting because this is the first time this kind of an outflow had been seen in a tidal disruption event. And it confirms this theoretical prediction that you would get a wind like this coming off when the accretion rate is this high. So even though we only have a few TDEs that are detected in the radio, we can already start to make comparisons to populations of other energetic transients that we know about. So this is a plot that basically shows the kinetic energy in the outflow versus the expansion velocity of the material producing the radio emission. So over here in the lower left corner, you have lower energy events like Assassin 14 Li. The blue stars are type 1 BC supernovae. We know that there are many supernovae, and long gamma ray bursts have been determined to form from the same kind of stellar explosion of the same kind of star as these type 1b/c supernovae, except not all stars, when they explode, produce a gamma ray burst. So there's kind of a distribution where the gamma ray bursts are the most energetic tip of the distribution of stellar explosions, and then you have the bulk of the population that don't manage to accelerate material to quite such rapid speeds. So there's sort of an analogy to be drawn between this larger sample of events of this different kind and the TDEs, where a few percent produce these strong relativistic jets and the bulk of the population just produce slower outflows instead. So we expect that we will find more TDEs with fainter radio emission as we continue to explore this fairly new area. The other exciting thing you can do with these observations is, because you have a outflowing material interacting with the surrounding medium, you can, it depends on what the density of the surrounding medium is, so you can actually build up a density profile around supermassive black holes and other galaxies where these TDEs occur at, this is normalized by the Schwarzschild radius of the black hole, but it's kind of parsec or sub-parsec scales. For the non-astronomers, that's about less than a third the distance from the sun to the nearest, or it's about the distance from the sun to the nearest star. So it's very small scales as the universe goes. But what's interesting is you can see that for Assassin 14 Li, because the material is moving more slowly, we're probing a very small radius, and there's a very steep density profile. This is about r to the minus 2.5. If you had a AGN accreting spherically, you would expect this density profile built up over time to be a little bit shallower, r to the minus 1.5. So this is perhaps indicating that there is something more interesting going on than simple spherical accretion in this black hole's history. So we'll have to build up our sample to see whether this steep profile is seen in all TDEs. In the jetted Swift event, which are these blue points here, there's kind of a hint that it's getting steeper at the smallest distances probed, but we really need to build up the sample to see how universally true this is. And in the meantime, it's just cool that we can do this in galaxies that are not the Milky Way with about the same spatial resolution as we can see in our own galactic center. So in summary, we've better constrained the fraction of TDEs that produce relativistic jets, and we're starting to think about, since we can constrain the physical properties in each case, what are the key parameters that actually determine whether a relativistic jet is produced or not. We've been able to measure what the density profile is around supermassive black holes and other galaxies, and the radio observations are a completely unique way of probing these events, and so it's very interesting to continue following them up, and that's one of the things I'll be continuing to spend a lot of time doing. So for the second part of my talk, I'm going to switch gears and talk about a second kind of extreme transient, namely gamma ray bursts, and some of the work I've done has started to answer some of these questions. So what is a gamma ray burst? Well, naively, it is a very bright flash of gamma rays. And they were actually first discovered in the 50s by the government, who were looking for evidence of nuclear explosions and other nuclear test activity by Russia, and then they started seeing gamma rays from the sky instead. So they didn't actually announce the discovery for a while after that, but after they did, astronomers got very interested and started building up a sample of these objects. We find there's two kinds of gamma ray bursts. There's short gamma ray bursts, which typically have a very hard spectrum and last less than 2 seconds. And then there's long gamma ray bursts, which are a bit softer and can last anywhere from a few seconds out to several hundred, sometimes 1,000 seconds. And we think that these two types of GRBs have distinct physical origins. So long GRBs are the ones that form when a massive star explodes as a supernova. And they're powered by a compact central engine, either the formation of a stellar mass black hole or some other compact remnant. And then short gamma ray bursts are formed when you have two neutron stars, or maybe a neutron star and a black hole, that are orbiting each other, spiral in, and collide. And so I'll talk a little bit about one project I did on each of these kinds of objects. So this is a physical picture of what's going on in a gamma ray burst. You have your material falling onto your central engine over there. And as it's falling on, the central engine accelerates a jet of particles out to nearly the speed of light. It's thought that there are internal shocks in this jet material moving at slightly different speeds running into each other that produces the gamma ray emission. And then this material continues moving out into the surrounding medium and produces a shock front at the front of this jet, which produces the synchrotron emission that we actually study in the radio through optical through X-ray band. This is called the afterglow, and it can last anywhere from a few hours to up to weeks or months in the radio band as the peak of that synchrotron moves down to lower and lower frequencies. So in order to fully characterize these events, as Ida said, you need a lot of observing time. In particular, these events were, until recently, less well characterized in the radio than in the optical and X-ray bands. And this was largely due to limitations of current facilities. There were some very detailed studies done, and going all the way back to 20 years ago now. These had been detected in the radio for a long time, but usually only at one frequency, usually with lower time sampling. So a couple of years ago, our group decided we were going to start observing GRBs as early as possible and get multi-frequency observations to really constrain what their afterglows are doing in the radio. And so we started out with these lofty goals of answering some of these questions, but I'm actually going to tell you about something somewhat unexpected that we found in one particular gamma ray burst, which was not one of these original things we went into this thinking we would find. So in particular, this is GRB 161219b, because it happened on 2016 on December 19th, and was the second gamma ray burst to occur on that date. So this is just a plot. Let's focus on the top half of the plot for now. This is just the flux density observed as a function of time. This whole observation took about 3 hours. And all of the synchrotron spectra that I showed are very slowly evolving as these things go. You would expect them to sort of change on hours to days timescales. Instead, we see that the flux density up at 20 gigahertz there has changed by a factor of 2 or more over about 20 to 30 minutes. So this is not expected in the intrinsic emission. So there must be something else going on here. We saw this and thought, this looks interesting. Let's investigate this a little bit more. Instead of just combining all the data we have at each frequency, let's split this up and look at the frequency in more detail. So each one of these colors is a different time slice. We started observing at the high frequencies and went down to low frequencies, but it shows kind of the same thing as the previous plot. Not only do we see these large changes in amplitude, we also see large changes in the spectral index. So if you look in the middle there, first when we started observing, the spectrum was pretty flat across in the yellow lines, and then after 20 minutes, it's changed to looking like this. So something is distorting this radio emission between the time when it was emitted at the GRB and when we're receiving the light from it at the telescope here at Earth. There's one obvious candidate for what could be doing this. It's actually a very similar related process to when you go outside and look at stars through Earth's atmosphere, you'll see them twinkle. It turns out that at radio wavelengths, we have a turbulent ionized gas in the Milky Way and the ISM. And this gas, since it's turbulent, has different clumps. And as your radio source comes in, radio waves come in from infinity and pass through these clumps, they can get distorted. And you can actually get an interference pattern like is shown here. And you can, if you're observing a single point on the sky, see large amplitude variations. So what's particularly unusual about this source is that the standard model for this particular line of sight through the galaxy would have predicted that the variations we saw would not have been quite so large in amplitude, and they would not have been varying on the same time scale. So what we interpreted this to mean is that our model of the Milky Way ISM along this line of sight was not completely correct. This is not entirely surprising because a lot of the sources that went into this model are from pulsar observations, which are concentrated on the galactic plane, and GRBs are uniformly distributed through the sky. So if you build up a large enough population of GRBs, you can actually start to constrain the properties of the Milky Way gas as well as the properties of the the gamma ray burst. So in this event, this effect has actually been seen in GRB afterglows going all the way back till 20 years ago, but this is really the first time that we had so much simultaneous frequency coverage, and we could really start to characterize the variability as a function of frequency and nail down some of these properties. So this, another smoking gun that this is in fact this scintillation event effect is that the radio source needs to be very compact for you to actually be able to see these large fluctuations, because otherwise light arriving from slightly different parts of the source will smear out this pattern, so you won't really see this effect. Now, GRB afterglows expand with time, so you would expect at some point the afterglow would be too large to actually continue to see this effect anymore, and you would expect that these large amplitude variations would actually quench at some point. And in fact, that's exactly what we see. This is the same thing, the light curve over about 3 hours, but this time at 8.5 days after the gamma ray burst was discovered. And we no longer see these large amplitude changes in the flux over very short time scales. You can see that all of the different frequencies, it's basically consistent with remaining flat. So we say that at this point, we have evidence that the afterglow has indeed expanded, and we can actually start to constrain how fast is it expanding? What is the size of the afterglow as a function of time? Which is really cool because our radio telescopes, although they're amazing, don't have high enough resolution to actually resolve the source, so it just kind of looks like a point source through your telescope. So we started doing this, using these properties of the scintillation, and when we observed it to quench, to measure the size of the source as a function of time, which is what you see with the black stars, and the uncertainty are the gray shaded bars here for this event, also compared to other GRBs in the literature. And by comparison, we have a model for what we expect the size of the source to be as a function of time, assuming that it is this relativistic fireball jet propagating out at nearly the speed of light. The model is from a companion paper by Tanmoy Lasker on that uses the radio, optical, and X-ray observations all together to characterize the properties of this event. And the interesting thing is that at early times, we actually find that the source size appears to be smaller than we naively would have expected from this model. So the model size does assume that when we're staring straight down the jet of the afterglow, we're seeing a nearly uniformly illuminated circle. So we're comparing the size you need for scintillation to occur to the full radius of the afterglow. However, it's possible that instead of a circle, you actually, if you could resolve the GRB afterglow on the sky, would see something more like a ring. These were some simulations done by Greneau et al. About almost 20 years ago, and they, in fact, predicted this is what the afterglow should look like. Since the disk is not fully illuminated, it turns out you would end up, if you assumed it was uniformly illuminated, underestimating the size of the source by a little bit. So maybe this is an indication that the source is not completely illuminated, and we're actually learning more about the geometry of the event itself, even though we can't resolve it directly. So if we do this kind of measurements for other GRBs and find that a lot of them show this smaller size at early times, that may be an indication we need to revise our standard fireball model, or it may be telling us that maybe we're not viewing the jet straight down the axis, but we're off a little bit. So these are results that are just being written up now, and if any of the astronomers in the room have thoughts, I would be happy to chat with you afterwards. So the final thing I'm going to talk about in this public section of my defense is going back to the short gamma ray burst population, and more broadly answering this question of what happens when two neutron stars collide. So on the left, I have some stills from the video that played in my very first slide at the beginning, and on the right, I have kind of a cartoon picture of what theorists think happens when two neutron stars come together. So you have your two neutron stars that collide, and it's thought that they will produce a relativistic jet, at least in some cases, that collimates material and accelerates it to near the speed of light, and this is what produces short gamma ray bursts. So if you're an observer and you're lucky enough to be staring directly down the axis of the jet, you would see the gamma rays. If you're off axis a bit, you wouldn't actually see this jet immediately because the emission would be relativistically beamed away from you. So you wouldn't be able to actually see the jet until it had slowed down and decelerated. So you would see the emission appear at later times. And if you are, so in the past, if the main way we were discovering these things was detecting short gamma ray bursts, we were seeing them all down the axis. But with, now that we have a new way of detecting these mergers through gravitational waves with advanced LIGO and Virgo, most of the events you're seeing are not going to be directly down the axis. So we're probing what's going on with the rest of this ejecta material. We know that there's also material thrown out at slower speeds, so it's quite possible that how fast the material is moving is a function of your viewing angle, and the slow-moving material in the bottom panel over there, and also this yellow shape here, that produces most of the optical emission, will eventually produce radio emission too, but on a much longer time scale. So this was the theory as it stood last fall, and then this fall, everyone in the field got very excited because we had the first chance to directly observationally test it. So in August, LIGO and Virgo discovered gravitational waves from this event called GW 170817. LIGO actually saw it and Virgo did not, which allowed them to roughly figure out where it was on the sky. Right after the gamma ray burst, right after the gravitational waves, we saw a very faint gamma ray burst. It's a lot fainter than, the gamma ray emission is a lot fainter than typical short GRBs, which we'll get back to. And then, so everyone got very excited, but then we had to wait for it to be nighttime in Chile, where all the good telescopes that could search this part of the sky were. And then within about an hour or so, 6 different groups had taken a picture of the host galaxy and discovered that there was an optical counterpart to this transient. And then once it was localized, everyone triggered deep X-ray and radio follow-up, which I'll talk about a little bit more. Just to better brag a little bit about our group's optical program, over on the left there in the blue and white contours is the region on the sky that the gamma rays and the gravitational waves limited the transient to. And then the red tiles are our pointings with our group's optical telescope, which we use the dark energy camera down in Chile. And the orange dot is where the transient was actually located. So this is a beautiful Hubble Space Telescope image that shows that the optical counterpart everyone got so excited about is that tiny little dot right there. But there's a lot of great science that came out of studying the optical observations, which I'm not going to go into because Phil will be defending his thesis next week, and you'll hear all about it from him. Instead, I'm going to talk about the radio emission and a little bit about the X-ray emission. So as Ito alluded to, as soon as we had discovered the optical emission from the source at a precise location, we immediately wanted to trigger radio observations. And at this time, the source was about to set in New Mexico. So we actually called up the telescope operator to find out exactly when the previous observation was going to end, so we knew exactly how much of a window we had. And turned out we had about 20 minutes as the source was just setting. So we've used the VLA to follow it right down to the elevation limit, and we got this image over here, which does not look very great because when you observe near the horizon, you have a very elongated beam shape and you have all these atmospheric effects. But nevertheless, we detected emission from the host galaxy of the transient, but there's nothing at the actual position of the transient itself. So right away, we knew that this was not like a typical short gamma ray burst where where with something this close, you would have expected to see bright radio emission immediately. So we already had a clue that we were probably not staring straight down the jet axis. We were off at an angle. And similarly, there was no X-ray detection at early times. So we started observing with Chandra, which is the most sensitive X-ray high-resolution radio, or the X-ray telescope in the sky. And at 2 days or so, we didn't see anything. And starting at about 10 days, an X-ray counterpart appeared at the location of the transient. So there's now rising X-ray emission that starts to appear at about 10 days. And then some work led by Greg Hallinan and Alessandra Corsi, they they detected the afterglow in the radio about 5-6 days later, which was shortly thereafter confirmed by our group. Our group also put in a program to observe this source with ALMA, and we did not detect anything in the millimeter band. But this is an image that Greg's team put together showing the initial non-detection in the radio and then the detection a few days after. So what can we learn from this rising X-ray and radio emission? Well, right off the bat, as I said, we can see that this does not look like any typical on-axis short GRB we've ever seen before. We saw rising X-ray emission instead of fading. We have the deepest early upper limits on the radioluminosity, which then starts to rise at late times. So right away, we can say that a typical on-axis jet from a short gamma ray burst of the typical energies we see in short gamma ray bursts is completely ruled out. So the next thing we explored is, well, what if there was a relativistic jet that was produced, but we're viewing it off-axis? So to figure out what the emission would look like in this case, we turned to simulations. These is some simulations led by a group at NYU, where they imagined a uniform relativistic jet just expanding into a uniform medium, and then you can integrate along whatever line of sight you want to figure out what your light curve looks like. And so in the paper that I led that we put out in October, we have all of these different off-axis relativistic jet models. On the left, there's sort of a very optimistic model and a very pessimistic model where this is taking the range of parameters that we see in short gamma ray bursts and comparing them. And you can see it in comparison to our upper limits. We really rule out an on-axis jet for pretty much any allowed range of parameters, and we start to rule out some of the other parameter space as well. And over here, here's our two detections shown with this uniform off-axis relativistic jet model. However, so this model accurately describes the first 40 days of observations and say, oh, well, there was a short GRB, it just was pointed away from us. But all of the models that fit the data predict that the radio emission should have very quickly turned over and started to decline. And instead, we've been continuing to observe this source, and the radio emission, instead of turning over and fading, has continued to get brighter. So what does this mean? This means that there can't just be a uniform relativistic core jet with all the material moving at the same velocity. It has to also be surrounded by some slower moving material. And in fact, this slower moving material is what's been dominating the emission that we've seen to date. And so it's actually unclear whether a successful relativistic jet was produced at all. You could either have a successful jet where someone in the universe saw a short GRB, but we didn't. But what we've been seeing is this slower moving material kind of surrounding the jet. Some people call all versions of this structured jet a cocoon model, where you have a cocoon of slower moving material. What I have called the cocoon model in this slide is the case where there was actually so much slower moving ejecta that the jet doesn't successfully get out. It's choked by the surrounding material. So no one in the universe saw a typical short GRB. Instead, the emission will be dominated solely by this mildly relativistic component. And so this, of course, it's very interesting to determine whether a relativistic jet was produced or not, because that has implications for the rates of these objects. It has implications for how we want to plan the follow-up in the future. And in general, observations like this are going to tell us a lot more about the lateral structure of the ejecta in these explosions, which constrains properties of the original central engine and so forth. So there's several models on this plot for the radio emission. The light blue models are from a paper I was on led by Raffaele Margutti, predicting that there was a successful relativistic jet and the radio emission should start to turn over pretty soon. Some of these other models that predict that there was no relativistic jet suggest that the emissions should continue rising for later times, although you can get a range of outcomes depending on exactly what parameters you pick. So we're continuing to monitor this source, and actually, just as I was writing up my thesis introduction, there was this paper by Doby et al. That was put onto, submitted to journals and put onto the archive that suggests that the radio observation, the radio emission from this source has started to turn over. So it was already kind of a hint, maybe here, that it was flattening or not rising quite as fast. But this, they did a statistical analysis here and showed that it really seems to be starting to turn over. So we will continue to monitor this source over the next few months and better constrain how fast it's declining, which will again have implications for which of these models is correct. So this is very much a situation where we want to say, stay tuned, and hopefully more will be known. So in summary, both long and short GRBs still have a lot to tell us. Long gamma-ray burst afterglows, some of them show much stronger scintillation variability than we expected, which is starting to potentially reveal interesting constraints on the emission models. And then the second key point is multi-messenger astronomy has arrived. We're now going to be able to constrain what goes on when two neutron stars collide with both gravitational waves and radio and other observations. And we're already starting to learn more about the structure of jets and outflows. And LIGO will turn back on at the end of this year, and we'll hopefully start to build up a much larger sample of these events and find out whether this event was typical or what the range of experiences are when this kind of event occurs. So this is my final summary. The first 3 points are the things I talked about. There were also some other long GRB results that I didn't have time to get into, but I'm happy to talk to people afterwards about more. And I just really think in general this is a very exciting time to be studying radio transients. We've got a lot of new synergies with observational facilities at other wavelengths that are continuing to get better and better. There are radio-only arrays that are going to start discovering lots of radio transients in real time within the next coming decades. And I think we really have a lot more richness to uncover, and I'm looking forward to continuing to working in this area. Thank you.
Thank you very much, Kate. We have time for a few questions from the audience before we take Kate away and grill her in person with a smaller committee. So, any questions?
Yeah. So in the interstellar scintillation project, how much do the uncertainties in the interstellar medium impact your inference on the GRB size?
Yeah, so that's what we attempted to indicate with the gray shaded bars in the size plot. Most of the uncertainty on that, so the properties of the ISM are actually directly constrained by both the frequency at which we observe that the variability peaks in amplitude and also the time scale of the variability. And so the uncertainties here are actually dominated by our uncertainty on the time scale of variability, which is then translated into an uncertainty on the ISM model. So if we had observed for longer, we weren't expecting to see this effect, so we didn't actually observe it long enough to see several full cycles of the effect, which would have let us get a very precise number for the time scale of the variability. In future events, we actually have a program approved on the VLA to do this project better the next time we get lucky enough to get a long GRB that's afterglow that's bright enough that we can just stare at it for 5 hours at a time. We should hopefully be able to tighten these error bars down a bit more. And start to build up a better model of the ISM at these higher galactic latitudes as well.
Okay, if not, let's thank Kate again.